And with that, we're going to go ahead and get started with Ms. Leila Meshkat, who's joining us from Goddard. And I've got her slides right here somewhere. Not those. So while she's talking, I'm going to stop my webcam up here so you all can see her. So welcome, Leila. Sorry about the audio problems today, but we're ready for you.
Good morning, everyone. Good morning. It's nice to be here. Um, so I'm actually calling you. I'm calling in from California, so JPL, and the topic of my talk is about command file errors. And the reason I call it an art and science is because you know, this is an area. Command file errors is something that that JPL has been dealing with over the last few years, and it's been a major challenge for us. And the work that IV&V has sponsored me to do over the last few years has really changed the way that we look at the approaches for managing command file errors in terms of using more advanced modeling and probabilistic approaches for doing that. So, and again, the reason I'm calling it an art and science is because the whole process of understanding what causes command file errors and what are the procedures, what are the processes that are already in place for dealing with them, and how we can really go into the teams and identify um, areas of improvement and identify technologies that could be used by the team members themselves to address this issue. That was kind of like an art. And as we go through the presentations, I'm going to talk more about this. So this is in summary, this is my outline. I'm going to talk about the problem, the approach, the summary of tools and techniques that I have created as part of this task, and then I'll get into a little bit of detail in terms of each of the tools and techniques and talk about how they work and how they've been applied. Okay, so let me see. Okay. So the problem that I've been dealing with is, basically my goal was to develop and infuse techniques to reduce the rate of operations errors, and I started at JPL. Nonetheless, all the technology that I have are applicable to NASA missions across the board, and also, okay, sorry, is it better now? Okay. So, okay, we just went ahead and adjusted the mute so that you don't hear my voice on two different medium and get and so that there's no echo. Anyway, as we were talking, the issue that I have addressed over the last few years is to develop and infuse techniques to reduce the rate of operations errors at JPL and at NASA. Now, what is a command file? A command file is a piece of software that is sent to the spacecraft, and the purpose of the command file is to, command and control the spacecraft. So, along with the avionics modules, the commands contribute to the whole command and control functions of a spacecraft, and they interact with the flight software. Okay. So the reason this became a big deal was because, we lost the spacecraft, the Mars Global Surveyor, to a command file error, among other things. So it was a combined failure, but one of the main elements of it was a command file error. And as we looked into our anomalies databases, we realized that command file errors account for an alarming fraction of the spacecraft anomalies and near misses. So then we determined, okay, we invest so much in the flight system itself, both the spacecraft and the flight software. And yet we are losing our spacecraft because of errors that are made on the ground in the process of writing commands and, radiating them to the spacecraft. So how do we address that problem? So that was the issue that was being addressed. Now, the way that the laboratory was dealing with that issue was that we were bringing in groups of people to have review boards and look into each of the command file errors and how they had been created and methods for improving the processes to prevent them. So in a way, the process that was being employed by the laboratory was not taking advantage of any advanced modeling approaches and what happens when you bring in a bunch of subject matter experts and have review boards, the information, there's so much second, third, fourth level dependency between all the different elements that are related to each other. And it's not really possible to hold all that information in your head as you're talking through them, as you're trying to come up with solutions. So it was clear to me that we need to use more advanced modeling techniques to at least capture all the knowledge that we have and try to reason about it. So in a nutshell, my first step was to start participating in these teams and trying to understand what it is that we're doing, and then try and understand, okay, how can I contribute to them in terms of using the techniques that I'm familiar with, that I've been working, in my career, and how can I apply them, or how can I come up with new techniques that are that can solve the problems in a better way. So in a nutshell, what was the goal? The goal was to enable projects to feel more in control of their command file errors and to make informed decisions to manage them. And so the first thing was to identify the key factors that lead to a command file errors, and provide a means for managers to assess whether or not their error rates are in range, and provide the tools and techniques for root cause analysis and mitigation planning. So this is, in summary, the different elements of the task that I worked on. So in order to identify the key factors that lead to command file errors, I'm going to call them CFEs from now on. So the first thing is, okay, what is it that causes CFEs? How can we manage it? How can we know that our rates are within range, or if something is off nominal? Because realistically, it's never really possible to get an error rate of 0. But what is it that we want to, it's always a trade-off. And so what I've been trying to do is to help people understand that, we make decisions that determine what rates we're willing to buy. So what are the trades that we have? What are the decisions that we're making? Can we make better informed decisions so that the rates that we're getting are consistent with what we are willing to accept? And then when, in fact, we have a command file error, how can we go back and do a quick root cause analysis? How can we understand why it happened and how to mitigate it? So these were some of the big questions that we were addressing. And to address each of these questions, I've developed a set of tools and techniques that I'll talk about. Okay. So this is the summary. This goes into a little bit more detail about the tools and techniques, and then I'll focus on each of them independently. And so again, I want to keep going back to my title. There was an art to this. There was an art to really going in and understanding, just being creative with the techniques that are applicable rather than having a pre-specified technique in mind. In fact, the first proposal that I wrote to the IV&V, I had a completely different idea in terms of the technique that I would use. But once I got into the team and started working with them and understanding the problem better, I realized that, okay, the technique that I had initially thought of is not the one that's applicable. So it ended up evolving into something different. And the reason for that was because, again, as I learned more about the problem, the solution to it changed. So this is what the solution has evolved into. And one of my objectives throughout the whole task has been to keep things really simple, because it's important for things to be simple in order for them to get infused. So in fact, the further along I went in the task, the more simple and, I would like to think, sophisticated the techniques became. Okay, so one of the tools that is actually a very simple Excel-based tool that has been the most valuable and has been infused easier than the rest of them is what we call the Sigma tool, which comes up with a distribution for the likelihood of command file errors. So what happens is that, given very few parameters in terms of the number of commands that we're sending to the spacecraft every month, every period, every time period, and certain characteristics during that period in terms of the novelty level of the mission, we can come up with a probabilistic distribution that can tell us what the range of errors will be for that duration of time. Now, the reason that they like this tool so much is that, number one, it helps people understand whether or not the errors they're getting is within range. And if it isn't, then they need to do a better root cause analysis to determine why. And it's, it's a visual tool, so it creates a visual distribution, and then they can compare it to what they're getting and see if it's okay. They can also use this tool to look into the past and see if, the error rates that they had in the past, which ones were out of range, which ones were smaller and bigger, and so on. So we'll get into the details of this tool shortly. The other tool which has come handy is a Bayesian belief network. And again, it's very visual and it looks pretty simple. You can, basically it's a network. You can identify a command file error and all the different root causes for it. And underlying the network, there's a solid probabilistic background and framework for it. So it's in order to enable reasoning about things that happen and doing root cause analysis. And again, the tool that I've been using for this is a freeware from UCLA, which is accessible obviously to all of NASA, and also my models will be available to NASA as per request, and also the models can be customized to the different applications and to the different systems that we have across the different NASA centers. Now, Bayesian belief networks use a lot of subjective judgment for building the underlying probability tables. What happened to me as I was going back and forth with the teams and using these networks is that people wanted empirical proof that the numbers, that the results we're getting from these models are correct, which is what caused me to do a bunch of empirical analysis. So the empirical analysis is based on looking at the actual data that we have in the PFR systems and building and looking at the statistics, doing different kinds of statistical tests and analyses in order to verify and validate the sigma tool and the Bayesian belief network. And so, so this has become a big part of the work over the course of the last few months, simply because the teams that I was working with wanted proof that the results are actually correct before buying into them and infusing it within their processes. Okay, so let's talk a little bit about the Sigma tool. Basically, we used Excel because it's cheap, it's multi-platform, everyone can use it. And the motivation for this occurred when one of the teams that I was working with was seemingly getting higher error rates per month for a few of the months. And they wanted to see if this is something they should be concerned about or not. And so what was very clear to me is that what they were looking at was that they were looking at the percentages. So for instance, if one month they sent 10 commands and they got one error, that means they had like a 1 over 10, 10% error rates, which was too high because the standard error rate is only 1%, for instance, at JPL. So is this something to be concerned about or not? And when I went into that team, it became clear to me that, well, they're kind of not looking at the picture, at the whole picture. In other words, the analogy that came to my mind is, okay, if we toss a coin, if we have, well, not a coin, if we, if we have like, if we roll a die and only 2 times, and one of those 2 times we get like a 2, does that mean that this die is not a fair die? In other words, when we don't have enough samples and we get a particular toss, that doesn't necessarily mean that our die is an unfair die. It just means that we don't have enough samples. In other words, getting 1 error in 10 commands doesn't necessarily mean that the error rate is high. It just means that we only had 10 commands. So it's still probably within the distribution that we had in terms of the 1% error rate. So I started modeling this with a binomial distribution as opposed to just looking at percentages. And then when I started modeling it with a binomial distribution, I looked into, okay, so how far are we really from the mean? We are still within the 1 or 2 sigmas of that mean. So this is why the tool became known as the Sigma tool. And this was very reassuring to the team that I was working with, because again, even though it's very simple, but they hadn't been thinking of it this way, and they weren't sure what to make of the, the seemingly increased error rates that they were seeing. So so this is basically what the tool looks like. And as we went on further, we further basically refined this tool in terms of the parameters that we were giving it. So as you know, a binomial distribution only really has two parameters. One is the number of tosses, and two is the probability for each toss to be a success or failure. So we had two parameters to work with and several different variables that we wanted to capture in these two parameters. And so one of them was the number of files that are being sent, so that was our basis. The other is the probability of error per file. Now, in order to get this probability of error, we had to look into several different factors. One was the base rate that we have at JPL, and several other factors in terms of, well, what does it depend on? How does this rate change over time? How does it change in terms of the novelty of the operations that we're conducting? How does it change in terms of the sophistication of the file that we're sending? Because not all files are equal. And I'll get into some of those details in terms of how we determine these parameters in the statistical analysis part of this presentation. But the bottom line, once we refine this, is that we get a very simple curve that tells us, so if you look into this chart right now, up to this point, up to the midpoint, is where we actually have data. Where you see the bars, that's the real data. The curve is the actual prediction based on the distribution. So you see that a lot of the bars that go up and down, they're actually consistent with the distribution. In other words, there's nothing to be surprised about. One or two instances, like in one instance, we have an instance where the bar is well above the curve. And when we looked into this a little further, we realized that this had to do with the data collection that was happening during that period. So again, very easily, just looking at this, the mission assurance manager can tell, okay, where am I sort of not okay? And then for that area, they look a little bit deeper to understand what's going on. And sometimes what's going on is very simple. So sometimes it just has to do, okay, did we collect the data properly as we were going through the mission? But sometimes it can be a little bit more complicated in terms of why were we having an increased error rate for a particular duration or for a particular period during our mission. So, and that would require a more in-depth analysis, which can be done with the Bayesian belief network, which we're going to talk about later. Now, the curve goes on into the future. So what happens here is that based on what we expect the mission profile to look like in the next, say, 24 hours, 24 months, we can come with a prediction in terms of what the error rates will be. So what this means is that if the project in question is not okay with these error rates, then they need to come up with a way to reduce them. But the point is that this puts them in control. So the idea is that we're not going to leave the error rates to just happen. We can predict them based on the characteristics of the project that we're working on. And if in fact what we're predicting is not okay for us, then we can look into ways to mitigate it or reduce the error rate, and we can do a trade analysis. Now, one thing to keep in mind is that most of the command file errors that we have are pretty benign. So it's only maybe a small percentage of them that cause safings. In fact, we've been looking at the percentage of command file errors that cause safings, and it's roughly in the order of 10%. Now, even if we do have a safing event, that doesn't mean that we're going to get into a critical state and we're going to have a mission failure. So safings can actually have a happy ending too. Most of the times they do. But nonetheless, this is a way to identify what the criticality can be. So what is the likelihood of getting into a safing situation if in fact we have a command file error, and then if we have a safing situation, there's a small likelihood that it's going to get into a critical state and things can get ugly. So again, the point is that this is something that we can control, and we make decisions based on which we have these rates, and so that's what gives a warm and fuzzy feeling to the managers, because they feel in control of what's happening. They don't feel that it's just up in the air and anything can happen. Okay. So here I'll talk a little bit about the empirical analysis before going into the Bayesian belief networks, and that's because it was the empirical analysis that helped us to refine the sigma tool in terms of the parameters that are used for the sigma tool. So when I show this to the managers, they tell me, okay, I see what you're telling me is going to happen in the future, but how do I know that I can trust your predictions? So this is what leads me to do the empirical analysis. Now, the data sources that I had for the empirical analysis included information about the command files errors that had been sent to the spacecraft in the past for the past missions, in terms of the number of blocks, the number of commands, and the number of files in each month of the mission, and the number of command file errors that were observed. I also had information about the activity levels in terms of the products produced by the flight team during each month, because one of the areas that I focused on was the operator cognition. And the idea is that the more stress that the operators are under, the more likelihood it is that they're going to make errors. So I wanted to see how much activity they had to do, like how much stress they were under in terms of the amount of work that they were doing. So I had a metric for that. I had a measure of how novel the operations were in each of the different months, in each of the time periods. And I had general information in the databases in terms of, what are the errors that have occurred during the life cycle of the flight project, and what are the details in terms of what their causes were and how they were mitigated. So the main goal of the empirical studies was to validate the results of the sigma tool. Okay, so are there questions? Okay. So, so we decided, so the first thing that I did was to look at the correlations. Okay, so what is the correlation between the number of command file errors, the number of files, commands, blocks, and activity levels? And what I realized is that the highest correlation was with the number of files that were being sent. The activity levels had, there were some correlation with the activity levels. Not so much. The correlations with the number of commands and blocks was not that much compared to the correlation with the number of files. So, but then they were not really insignificant either. And when I looked at it a little bit deeper, I realized, well, there's quite a bit of correlation between the number of files and the commands and the blocks and commands within the files. So what I'm getting here is that on one hand, files are not equal. So when we use a binomial distribution, we assume independence between the trials. So all the trials are independent and equal. Now, is this really true? So that was something that I was questioning. And when I just enter the number of files, I'm kind of assuming that all the files are equal, but then they're really not, because files can have different number of commands and different number of blocks in them. So some are more sophisticated than the others. What I realized, though, is that what's most significant is the number of files, not so much the density of commands in the files or the number of modules that there are in the files. So what this tells us is that what happens in the process of putting a file together and radiating the file, the likelihood of infusing errors into that process is more so compared to the likelihood of having errors within the actual commands. In other words, the recommendation that came out of that is to have smaller number of files. So the more dense the files are, and the lower number of files that we have, the less errors we're going to have, because most of the errors are associated with the files rather than the number of commands within the file. So this was one finding. And so I did a whole bunch of different experiments. So the first thing was to do a little bit of phasing to see. One thing which was a surprise was the rather low correlations with activity levels. So I was expecting that to have a higher correlation. We were expecting it as a team. As I was talking with the operators, we were expecting activity levels to be a driver, and it wasn't. So we thought the reason might be because the activity level in one phase would show its effect in the next phase. In other words, if we had a very high activity phase, the commands in that phase were being sent in the next phase, so the errors would show up in the next month. So I did a little bit of phasing with the data to see if that changes the correlation. It didn't. It did not change the correlations. So, these were the initial parameters that we looked at, but then someone, actually the team member that I was working with, Bruce Wagner, came up with the idea of, okay, let's consider novelty factor instead of activity levels. In other words, instead of looking into how busy the team has been, let's look into how novel the operations were in each phase. And by the way, looking at the lack of effective activity level, as we discussed it with more of the team members, it became clear that the reason activity levels were not that much of a driver, actually we had a summer student dig into the FTEs, the full-time employees that were working on the project in each month of the project, and we realized that what the project had done is that it had offset the high activity level with more staffing. So it wasn't necessarily a matter of looking at just the activity levels. It was a matter of looking at the activity levels per person, and that was almost constant. In other words, the project had done a really good job of managing the activity levels of the employees so that they don't get too stressed out and make errors because of that. So that was the reason that correlation with activity levels was low. And so, so that was something, it was a surprise initially, but then we kind of found out why that's happening. So anyway, at some point we decided to look into the novelty factor, and then the novelty factor turned out to have a very high correlation also. Okay, which tells us that when we have sophisticated operations, or when we have operations which we haven't done before, so for instance, when we're having an encounter, or when we're in the very early phases of the mission where everything is novel, those are areas where we're more likely to have errors. Now, this is just a chart to show you, and this is something that I did in the R statistical software, which is a freeware, RStudio, just to look at the correlations between these different variables. And as you can see, commands, blocks, and files are highly correlated with each other. So the question is, can we reduce these three variables to one? In other words, going back to the discussion about the files not being equal, well, it's true the files are not equal, but how can we equalize them? In other words, how can we come up with a variable that can take into account the variability of all these three variables? So for that purpose, I did some principal component analysis and some factor analysis to come up with some adjustment to the number of files. So what I got then was an adjusted number of files. Okay, so in other words, what we learned is that amongst these three, amongst the number of files, the number of commands, and the number of blocks, the variable which had the highest effect, most effect, was the number of files. But commands and blocks within a file are not completely irrelevant. So if in fact a file has more commands and more blocks, we need to adjust it a little bit to take that into consideration. So what we can do for the binomial distribution is, instead of giving it just the number of files, we can give it an adjusted number of files, which is a function of all these three variables. And to find that function, I used a bunch of different techniques, principal component analysis and factor analysis, which I've written them up in a paper. I'm not going to get into the details of it right now. But the idea was to come up with a way of taking these dependencies into consideration with one variable instead of three, because the three of them were highly correlated. Okay, so we ended up with one variable for the number of files and one variable for the novelty level. Okay, and the way we took this into account was that for the number of trials in the binomial distribution, I used the adjusted number of files, and then for the probability of error per file, that would depend on the novelty level. So we have different base rates at JPL, which correspond with the different novelty levels of the mission, and then based on the level of novelty that we're expecting to have in the mission, the distribution for the error changes. Okay, so this was some of the correlation analysis. And then, of course, I also did a bunch of regression analysis just to understand, how much of the variability can be explained with these variables. And then I also did a chi-square test, goodness of fit test, because one of the questions that was posed to me is that, well, how do you know that the binomial distribution is actually the right distribution? The reason I had picked that distribution is because the behavior of the system, to me, mimicked a binomial distribution. But then in order to prove that it's correct, I just used the chi-square test, which is, it's a standard goodness of fit test. And so when I did that, I got a p-value which was such that I could not reject the null hypothesis, which indicated that this was the correct distribution. Nonetheless, I was able to adjust my my parameter in the binomial distribution just a little bit to get an even better p-value. So it's always helpful to look at the problem from multiple dimensions. And actually, that's part of the art piece, I believe, of this whole effort, to be open to looking at the problem from multiple perspectives. And again, so between the regression testing, the chi-square testing, the principal component, and the factor analysis, I kind of was able to scope the problem and to basically bound it. Okay, so now I'm going to, so this is a little bit of information about the principal component analysis that I just mentioned to you, and now I'm going to talk a little bit about the Bayesian belief networks, just because I know we're kind of running, we don't have too much more time. Okay, so so far we talked about the sigma tool and some empirical analysis, and the idea with that is very simple. We come up with a distribution for the expected number of errors based on the number of files that we're sending, the correct characteristics of these files, and the novelty levels within the operations that we're doing. Nonetheless, there's so many different things that can cause command file errors. And as we look at the the databases that we have, the problem failure reports that we have, and also as we look at all the different, all the work that the laboratory has done over the years in terms of putting together review teams and doing root cause analyses, that there were so many different causes for errors. So the question was, how could we summarize all these causes and put them in a model, in a simple model that can be used for reasoning and root cause analysis? Okay. In a nutshell, this is what the abstract model looks like. We have command file errors that are caused either by slips or mistakes. And the difference between a slip and a mistake is when the operator, it actually doesn't know that what they're doing is wrong, right? So it's kind of, they don't understand the state of the system, or they don't understand the effect of the command that they're going to be sending. So it's not just an oversight, it's actually a mistake when there's a lack of understanding of what's happening. A slip is when there's just kind of a little oversight somewhere. So sometimes we have situations where someone sends a command twice, or a command that should have gone at a certain point in time goes at a certain other point in time. So it's not because of a lack of understanding of the system or of what's going on, it's because of a simple oversight, and that happens too. Now, either slips or mistakes can happen because of what we call the mission system, and the mission system is comprised of the flight software, the ground software, the simulation, the test beds, all of these things that are actually, that we're calling the hard factors, that are actually in existence and they're actually tangible. Or it could happen because of non-tangible factors, which is the operator cognition, and anything that can contribute to the operator cognition, such as communication, such as management, all of these we just classify them into soft factors. So I'll get a little bit more into the details of what these things are, but this is the high-level abstract model. Okay, so this is a little bit more detail. So as we mentioned, either mistakes or slips can cause a command file error. And both the hard factors, which is the right branch of this tree, and the soft factors, which is the left branch, can contribute to either mistakes or slips. Note, however, that the contribution of the soft factors to slips is higher, and the contribution of the hard factors to mistakes is higher. So if we go, so this is the, this is the network, but underlying each of these nodes, there's a probability table. There's a conditional probability table, which identifies the probability of the node occurring based on the arcs that are coming into it from the other nodes. Okay, so on the right side, we see the mission system, and the mission system has to do with the process procedures. And again, this model is slightly different for each flight project. I've built the model for several flight projects now, and this is for a particular flight project. For this particular flight project, the documentation of the mission system was pretty significant because the flight system was built by a contractor, and so the lack of documentation actually, and then we at JPL were operating the flight system, so the lack of documentation was one of the factors in command file error. So again, these nodes can be slightly different for different flight projects, and the idea is to customize them as we're working with different flight projects. Process procedure software, both the ground software, the flight software simulation. So for this particular flight project, that was not a big deal, but I have had a different project where the simulation test beds, they were producing a lot of false positives. So, so people were not paying so much attention to the results of the simulation anymore, and therefore the actual errors that we were seeing in the simulation actually caused command file errors, and they were not caught early on because of the lack of because of the lack of user friendliness really of the simulation test beds. So again, these are some of the these are some of the elements that can contribute to a mistake. The elements that can contribute to the operator cognition, this is how we characterize them. On one hand, it could be the skill level of the operator. So the more skilled, the more training and experience the operator has, the better the operator can understand what's going on. This situational awareness, this turns out to be very significant because sometimes what happens is that operators, for instance, in the case of one flight project, the operator spent a very small percentage of their time on that particular flight project. So they had a hard time catching up with what's going on for that flight project as they were, transitioning from a different task to this task. So they had little situational awareness. And some of the elements that contribute to situational awareness are communications with the external team. So especially when we have distributed teams, that happens where people in one center are not clear about what's going on in some other center, or there might be internal communication issues, and that is often driven by management and organizational factors. So often it's management that makes decisions that impact the communications between teams, or management makes decisions in terms of how much information the operators actually need to have, and that's a really important decision because if they have too much information, they get overwhelmed. If they have too little information, they don't have necessary situational awareness. The operational complexity we summarized into the development activity level and the command frequency level. Okay, if we move on, so this is kind of a blow up of the operator cognition, the left-hand side of the tree, and this is a blow up of the right-hand side. So again, for the right-hand side, the ground software and flight software, we identified that the root cause for all the errors that are because of the flight software or ground software can go back to either the coding, the requirements, or the configuration. The simulation, we determined it either has to do with the utility of the simulation test beds. So for instance, in the case where we were getting a lot of false positives, it was just really hard to use the simulation tools, right? So because of that, people weren't paying attention to legitimate errors that the simulations were showing. Sometimes the issue is that it's not maintained properly. In other words, the simulators don't necessarily reflect the latest state of the spacecraft. So that can be a problem because then there's this lack of consistency between what the simulators are telling us and what's happening on the actual spacecraft. And then the fidelity. So sometimes the level of fidelity is too low or too high. So if you get too much into the details, you get lost. If it's too low, you don't understand quite what's going on. So again, these were some of the factors. Yes, so I understand. So I need to be really fast. Okay. So I'm going to talk about a couple of use cases that I did with the BBN models, and then I'll wrap it up. So, okay, the numbers are not coming, the bars are not coming across in these charts. Nonetheless, so for instance, I did a test to look into the effect of management on the command file errors. And so when management was adversarial, it can cause a significant increase in command file errors even during low activity. So I set the activity levels to low, and the command frequency to low, and management to adversarial. So these were the different states, and the likelihood of slip and command and went up from 1 to 1.54%. These were just some use cases, right? So let's look into some other use cases. And then if we look at the same system for teaming management, the slip, so it goes from 1.57 to 2.25. I'm sorry, so that was the difference between adversarial versus teaming management. Now let's look at a different use case. So this is to understand, to do some root cause analysis. So this is where we looked into, okay, let's assume that an error has occurred, and let's roll back and see what is the most likely cause of the errors. And so, for instance, if the mission system was inadequate, then what is the likelihood that the simulation is inadequate? And the simulation is inadequate, what is the likelihood that it's because of hardware simulations versus software simulations? So when something happens, you can go back and determine, okay, what is the most likely cause of what just happened? And so this helps with root cause analysis. And let's see another use case. This was the probability of key nodes during the different mission phases to understand, okay, what is the likelihood of each of these things happening during the early phase versus the cruise phase? And I think I have a chart on that. And so this tells you how things change during the different phases of the mission. And in the case of, so these use cases are from different flight projects. In the case of this flight project, the main driver was the operational complexity was really high, especially in the early phases. So this kind of helps you determine when you use this in combination with the Sigma tool. So the Sigma tool tells you, okay, you're going to have such and such error rate. And then this tells you what the error rates are because of. So that's the other part of managing the command file error rates, right? You come here and see, okay, what can I attribute my error rates to during each phase of the mission for each project based on the customized BBN model that I've built for that project. And then you can go back and say, okay, so where do I go in my system to reduce the error rates for that particular project during each phase? And then this is a little bit of a sensitivity analysis. So for this particular mission, it was really interesting because the interaction effects were really high. So for instance, the particulars, when we went into the details of the simulations or the ground software, that each of the elements did not have a very high sensitivity. But for instance, the ground software had a much higher sensitivity to each of its elements. So that indicated to me that, that there was a lot of interaction between the coding, the requirements, and the configuration that caused the ground software to become so sensitive. So that's a little bit of a sensitivity analysis. So my point here with these use cases is to show you the different types of studies that we can do once we've set up the Bayesian belief network model and we've given it all the probabilities. And then improvement potential. This was another one which is quite interesting. So even though something might be very sensitive, that doesn't mean it has a lot of room for improvement. Because in some areas we actually do really, really well. So this is another study that you can do and say, okay, so for instance, in this project, operations complexity was the one that was most sensitive, but the procedure utility was the one that had the most improvement potential. So in other words, you can understand where is it that I'm most sensitive, and then where is it that I can create the most the biggest, the biggest improvement in terms of improving the overall rates. Okay, so in conclusion, and there are two main elements. So again, based on all these studies, what we've concluded is that there are two main elements that contribute to command file errors: the base rate, which is dependent on the underlying infrastructure, and variations to this base rate, which are driven by the characteristics of the flight project in question. And the managing of the command file errors requires the development and customization of, different tools and technologies in order to do so. So that's the simple conclusion from all these studies. I'm happy to entertain any questions. Hello? Yes, I can hear you.
Yeah, just a question. I guess going back to your Excel tool, where you were just looking at the range, taking a step back from a risk perspective, that only perhaps 10% of those will report any kind of critical error. Do you ever do analysis on that 10% as far as probability, likelihood, ability, tax? Is that some kind of analysis you'll plan on doing? I see you going across the board and looking at this sector, but I guess from another perspective, okay, there's only 10% that really falls critical to happen. Perhaps we do some analysis on that as well.
And Jennifer, I think you hit it right on the head. That's the holy grail. So that's what the projects want to know. In other words, when you ask them how much are you going to buy into it in terms of making command file errors, they say, well, that depends on what the effect of the error is. If in fact it's going to be a critical error that causes safing, I want to reduce that to zero. But and I'm willing to pay for it, whatever it takes. But if it's a non-critical error, well, there's only so much we can do. So yeah, that's a question I have pondered. I don't really have a good answer to that question. So in other words, if we could tell whether the error rates that we're expecting are going to be critical or non-critical, that would be very useful to projects. But at this point, I don't know exactly how to analyze it actually, because I just know the percent. We can look into the PFR databases and identify, okay, what is the percentage of errors that cause safing? Now, I think what you're suggesting is, well, can we come up with some other characteristics? Can we analyze this and say, okay, what other characteristics do errors that cause safing have? And so how can we go about preventing those? And so that's a really good question. It's a question I do not really have an answer for. And I recognize that that is the Holy Grail, and that is what the projects want to know. Yeah, but so I just don't know. If we could tell whether or not this error rate is going to be associated with something critical, then we would do everything in our power to prevent it. But how can we tell? I don't know.
Well, we've pondered it in other fields as well and kicked around some suggestions. So we've kind of gone in circles just as you have with the thinking. So I figured to put it out there because I saw it in here as well.
Well, yes, and
in fact,
if anyone has any suggestions, or I would love to hear that. And if you have any publications, any pointers to how I might learn more about what other people have been thinking and doing about it, I'd love that.
Great, thank you.
Thank you.
Okay, I think we're just going to go ahead and move on. If we have any other questions for Leila.